Welcome to the final series on long transmission lines. Unlike the previous session, where we used the rigorous method to solve problems related to long transmission lines, today we will continue with similar problems but apply hyperbolic functions expressed in terms of exponentials. That said, for comparison purposes, we will use the same problem we analyzed last time out and see if we arrive at the same result. So, without any further ado, let's get started.
Recalling the earlier equation, consider a three-phase transmission line that is 320 kilometers long with the following parameters. Resistance per phase per kilometer, 0.075 ohms per kilometer. Inductance per phase per kilometer, 0.48 times 10 raised to power minus 3 Henry per kilometer. Capacitance per kilometer, 3.38 times 10 raised to power minus 9 farad per kilometer. 1. Determine the exact ABCD constants for the line using the above parameters. 2. Using the ABCD constants, calculate the sending end voltage and current when the line is delivering a load of 480 megawatts at a lagging power factor with the receiving end voltage maintained at 330 kilovolts. 3. Finally, determine the voltage regulation and efficiency of the transmission line.
Referring to our previous series, we have already calculated some values, which include the impedance, admittance, and gamma L. The characteristic impedance, ZC, was calculated in the later part of the video. However, we will calculate it again here, as it is a value we will refer to in subsequent steps. So the characteristic impedance, ZC, is given by square root Z all over Y equal to square root of 53.66 at an angle of 63.43 degrees, all over 3.39 times 10 raised to minus 4 at an angle of 90 degrees. The result of it will be this here. And finally, characteristic impedance ZC will equal to 397.86 at angle of minus 13.29 degrees.
So using the exponential formulation, cosh gamma L is equal to e raised to power 0.0309 at an angle of 7.51 degrees, plus e raised to power minus 0.0309 at an angle of 7.51 degrees, all divided by 2. To convert this to rectangular form using Euler's formula, we need to recall that e raised to power alpha at angle theta is equal to e raised to power alpha times cos theta plus j sine theta. Now applying this, e raised to power 0.0309 at an angle of 7.51 degrees becomes e raised to power 0.0309 times cos 7.51 degrees plus j sine 7.51 degrees. Similarly, e raised to power minus 0.0309 at an angle of 7.51 degrees becomes e raised to power minus 0.0309 times cos minus 7.51 degrees plus j sine minus 7.51 degrees.
Again, we should note the following identities. Cosine negative theta equals cosine theta. Sine negative theta equals negative sine theta. Also, we have the following evaluated constants. E raised to power 0.0309 equals 1.0314. E raised to power negative 0.309 equals 0.9696. Cosine 7.51 degrees equals 0.9914. Sine 7.51 degrees equals 0.1306. So when we substitute these values into the expression, we get the following result. Upon expanding, the left-hand side becomes 1.0222 plus j 0.1348.
Likewise, for the right-hand side when substituted, we will obtain the following expression. Upon expanding the brackets, we will arrive at this result. According to the equation for cosh gamma L, which is given by Euler's formula as cosh gamma L equals e raised to power gamma L plus e raised to power minus gamma L divided by 2. We can proceed with the substitution accordingly. When simplified, cosh gamma L becomes 0.9917 plus j 0.0041. Finally, when converted to polar form, the result is 0.9917 at an angle of 0.237 degrees.
In the same vein, sinate gamma L can also be determined. Since we are working with the same values as before, there is no need to go through the entire process again. The only difference lies in the numerical sign here, which changes from plus to minus. When substituted accordingly, we have this here, and when further simplified, the expression becomes 0.061 plus j.2615, all over 2. So, sin 8 gamma L equals 0.0305 plus j.1307. When converted to polar form, sin 8 gamma L equals 0.1342 at an angle of 76.86 degrees.
Now that we have determined the values of cosine gamma L and sine gamma L, we can proceed to use the ABCD parameters to calculate the sending end voltage and current of the transmission line. We know that A is equal to cosine gamma L, which we already have. B is equal to the characteristic impedance, ZC, multiplied by sine gamma L. C is equal to 1 over the characteristic impedance, 1 over ZC, multiplied by sine gamma L. D is the same as A.
To calculate B, which is the characteristic impedance ZC, we use the previously determined value. ZC equals 397.86 at an angle of negative 13.29 degrees, and sine gamma L equals 0.1342 at an angle of 76.86 degrees. Multiplying both gives B equals 53.39 at an angle of 63.57 degrees. Similarly, for C, it is computed as C equals 1 raised to ZC times sine gamma L. When evaluated, we get C equals 3.72 times 10 raised to power negative 4 at an angle of 90.15 degrees.
Now that we have all the ABCD parameters calculated, we can proceed to solve for the sending end voltage Vs. That is, Vs equals A times VR plus B times IR. When we substitute the values, we have the following expression. After multiplying the like terms, we get 188,944.22 at an angle of 0.237 degrees, plus 51,535.23 at an angle of 34.03 degrees. Before we can add both phasors together, we need to convert them to rectangular form. After conversion, we obtain Vs equals 231,652.146 plus J 29,622.52. Finally, when this is converted back to polar form, the sending end voltage Vs is 233,538.396 at an angle of 7.28 degrees.
The sending end current, Is, can also be calculated as Is equals C times VR plus D times IR. Substituting our values into the equation, we will obtain the following expression. Upon multiplying like terms, we arrive at the corresponding results. Since the terms need to be added, we first convert them to rectangular form. After conversion, the expression becomes this here, and when added, we have 834.618 minus J 404.216. Converting this back to polar form, the sending end current, Is, is 927.349 at an angle of minus 25.84 degrees.
Perfect. Now, comparing the value obtained here with the result at the other end in the previous series, we observe that the difference is not significant. In fact, it is almost the same. Back to question 3. We will now calculate the line regulation and efficiency of the line. For the line regulation under no load conditions, the sending end voltage Vs divided by A minus VR divided by VR times 100. When substituted with actual values, we arrive at the following. After simplification, we get a result that is equal to 23.60%.
The efficiency of the line can also be calculated. It is given as the receiving end power PR divided by the sending end power PS multiplied by 100. So sending end power PS equals root 3 times 407,885.818 times 927.349 times cosine theta. To determine theta, we add the angles of the sending end voltage and current, that is 7.28 plus 25.84 equals 33.12 degrees. Since cosine 33.12 degrees equals 0.83, theta equals 0.83. Substituting this value into the equation, we get sending end power PS equals 543,776,622 watts. Now, dividing by the receiving end power, PR, that is 480 megawatts, and multiplying by 100. 480 million divided by 543,776,622 times 100 equals 88.27%. Therefore, the efficiency of the line is 88.27%.
Now that we have used all the known methods to solve for long transmission lines, it is important to note the following. The convergency series method is best suited for situations where a quick manual approximation is needed, making it ideal for academic exercises or low-resource settings. The hyperbolic of exponential method is more appropriate for longer lines, especially when dealing with complex propagation constants. It is most effective when using calculators or software tools, as it involves expressions like e raised to power gamma L and e raised to power minus gamma L. Finally, the rigorous method is the most comprehensive and accurate. It is recommended for critical real-world applications where precise modeling is essential, such as in simulations, protection design, and detailed transmission line studies. And that is it for today's series. In the coming series, we will be analyzing load flow of the line using the Newton-Raphson method. So until then, peace.